In section 7.3, we're going to expand our horizons a bit as we study logarithmic and exponential functions with other bases. When your exponential function or your logarithmic function has a base of e, then the derivatives and integrals are pretty simple and straightforward. If you have a base other than e, then you're going to have some extra constants to deal with, both with differentiation and integration. Let's begin with the rules of differentiation. Just a quick review, we have learned that the derivative with respect to x of e to the x is e to the x. So if the base is something other than e, such as b, where b represents a real number, then the derivative with respect to x of b to the x is, we're going to make a copy of the exponential exactly as it appears, kind of like we did with e's, but we are going to multiply by natural log of the base. Now let's see where this formula comes from. We're going to start out with an exponential function with base b. So b has to be greater than 0, b can't be equal to 1, all of the ordinary stipulations for exponential functions. Now let's go ahead and take the natural log of both sides. So we have natural log of y equals natural log of b to the x. By log properties, we're allowed to move that exponent down in front as a coefficient. Then we will differentiate both sides of this equation with respect to x. Notice the mismatch in variables. We're differentiating with respect to the independent variable x, but I do have a function of y here. So this, of course, is implicit differentiation, or really my whole technique here, of course, is logarithmic differentiation. So when I differentiate natural log of y with respect to x, I'm going to end up with 1 over the argument of the natural log times the derivative of that argument, which we can express as dy over dx. On the right side, I have an x times a constant. Remember, if b is a constant, then natural log of b is a constant. So the derivative of a constant times x is the constant, right? If I'm looking at the derivative of a constant times x, the derivative is the constant. So if my constant happens to be something like natural log of 2, then the derivative is just that constant. So the derivative of x times constant natural log of b then is natural log of b. Let's go ahead and solve for our derivative term by multiplying both sides by y. And then, as we ordinarily do with logarithmic differentiation, we're going to make this an explicit derivative by replacing y with its original expression in x. So we can replace y with b to the x, and we have derived our derivative formula. So again, the derivative with respect to x of an ordinary exponential, natural exponential, is e to the x. But if the base is something other than e, I'm going to make a copy of the exponential and I'm going to multiply by natural log of the base as an adjusting constant. Now, the chain rule applies both to our natural exponential and also our exponential functions with bases other than e. So if I need to differentiate with respect to x, b to the u, I'm going to make a copy of the exponential exactly as it appears. I'm going to multiply by natural log of the base, just like I did with the ordinary case, but then I'm going to multiply by the derivative of the exponent with respect to x. Okay, what we have up here is a function of x, so this represents the derivative of that function of x. Now, take a little bit of time to memorize that formula. It is something that's easy to forget, and it pops up in random places, so be prepared for that. Let's practice finding the derivative. We want to find the derivative with respect to x of 2 times 3 to the x. Well, the coefficient 2 there is simply a coefficient that's going to filter through to the derivative. Then I'm going to make a copy of the exponential exactly as it appears, and then multiply by natural log of the base. And that's as good as it gets. There's nothing I can do to simplify that. Make sure that you are not tempted to call that 6 to the x times natural log of 3. Did anybody think that? Of course not, because we know that the order of operations says I must evaluate the exponent before the multiplication. So if I multiply the 2 and the 3 together, I've evaluated the multiplication before the exponent, and we violated the order of operations. So be careful about that. Don't be tempted to do that mistake. Let's move on to our next example, the derivative with respect to x of x squared times 2 to the x. Notice we are dealing with the product of two functions of x, hence we will need the product rule. So we're going to write the first function, x squared, and then we're going to multiply by the derivative of the second function. The second function is an exponential function with a base other than e. So we make a copy of the function and multiply by natural log of the base. Continuing with our product rule, now we're going to find the derivative of our first function, 2x, and then we're going to keep the second function the same. Again, I can't combine those 2's. One has an exponent that takes priority. But we can simplify this expression. Notice we have two terms. Here's our first term and here's our second term. We can simplify this by factoring out the greatest common factor. Notice both of those terms have at least an x and a 2 to the x term. So if I extract that from the first term, what's going to be left behind is x times the natural log of 2, and taking it out of the second term, we just end up with 2. So it's always a good idea to simplify your derivative by factoring. Looking at example C, we have 500 times 1.05 to the 2t. 500, of course, is just a constant coefficient, which we filter through to the derivative. Then, to differentiate the exponential function, we're going to make a copy of the exponential exactly as it appears, and then we're going to multiply by the derivative of the exponent, which will be 2. Now, the 500 and the 2 are compatible, so we can multiply those together and call this 1,000 times 1.05 to the 2t, and that is our derivative. Back up here to the other side of our page, we can work example D, y equals 3 to the 2x. Now, we don't have our derivative denoted here. You can call it y prime, you can call it dy over dx, but we are differentiating an exponential function with a base other than e. So we're going to make a copy of the exponential exactly as it appears, and we're going to, don't forget your natural log of 3. I just realized Three, 2, 1. We have 500 times 1.05 to the 2t. So we're going to filter that constant coefficient 500 through to the derivative. Then we're going to make a copy of the exponential function exactly as it appears. But because the base is something other than e, we're going to need to multiply by natural log of the base. Now, we're not quite done yet because the chain rule says we also need to multiply by the derivative of the exponent, which is 2. So to clean this up, I'm going to multiply compatible numbers. Notice we've got 4 factors here. The 500 times 2, those are compatible factors. I can go ahead and multiply those to get 1,000 times 1.05 to the 2t times natural log of 1.05. And that is our derivative. Let's work our way back up here to the other side of the page. Example D is y equals 3 to the 2x. The problem is to find the derivative. This time we don't have our differential operator, so you can call it y prime, you can call it dy over dx. Either of those would be acceptable. So this is an exponential function with a base other than e. So the derivative starts with a copy of the exponential function. We're going to multiply by the adjusting factor, natural log of 3, and then we're going to multiply by the derivative of the exponent. Now, there's nothing that I can simplify or combine, sort of like the order here. Maybe bring the 2 over to the left, as long as you're not tempted to multiply it by the 3. Either of those two lines would be perfectly acceptable. Notice on example E, to find the derivative, we are going to need to apply the quotient rule. So the derivative of y begins with squaring the denominator. So I'm going to write 5 to the x over 2 squared. Remember, whatever term you square in the denominator, that's the term that you lead with in the numerator. Then we're going to multiply by the derivative of the numerator. The derivative of sine of 3x is cosine of 3x, but we need to multiply by the derivative of the argument, which is 3. Minus, now we're ready for the derivative of the original denominator. It's an exponential, so we make a copy of the exponential. We multiply by the adjusting factor, natural log of the base, and then we multiply by the derivative of the exponent. The derivative of x over 2 is 1/2. Finally, we multiply by the original numerator. So we are finished with the differentiation. Let's see if we can simplify this. Notice in our numerator here we do have 2 terms, and I spy that 5 to the x over 2 is common to both of those terms. So I'm going to factor it out as a greatest common factor. Notice what's left out of that first factor is cosine of 3x times 3. I'm going to move the 3 to the left, call it 3 cosine of 3x for readability. And then we have 1/2 natural log of 5 sine of 3x left from that second term. On the bottom, we're going to multiply the exponents. Remember, when you raise one power to another power, you multiply the exponents. So we end up with 5 to the x. Now, it's looking better, but we're not quite done simplifying. Notice here we are dividing like bases. When we divide like bases, we can find the difference in the exponents. We're going to go ahead and write this with positive exponents. So notice that the difference between those two exponents is x over 2. 1 minus 1/2 is 1/2. But the biggest number's in the denominator, so the leftovers are going to go in the denominator. So when we cancel these, we're going to end up with 5 to the x over 2 in the denominator. Also, this is technically a complex fraction because I've got a fraction in the numerator. So to clear that, I'm going to multiply the top and the bottom by 2. Got to distribute it here and here. That way we'll have just a double-decker fraction. So our result will be 6 cosine of 3x minus natural log of 5 sine of 3x divided by 2 times 5 to the x over 2. So I think I mentioned before that sometimes the algebra part is more technical than the calculus part. Let's finish with f of x. We'll call the derivative f prime of x. Make sure you do label your derivative. I don't just want to put an equals here because what I'm about to do is not equivalent to f of x. It's something new, so I have labeled it with f prime of x. Because it is an exponential function, we make a copy of the exponential function exactly as it appears. Because the base is something other than e, we multiply by natural log of the base. And then because the exponent is a function of x, we also multiply by the derivative of that exponent, which happens to be negative 2x. And that's pretty readable. That would be acceptable, or you may want to call it negative 2x times 7 to the negative x squared, natural log of 7. Now that we have a little bit of practice under our belt, let's compare some problems which can challenge our understanding of these formulas. Sometimes we have to distinguish which rule we're going to use. So on these examples, we're just finding the derivative. Example A, we want to find the derivative with respect to x of e to the e power. Notice the base, e, is a constant. The exponent e is a constant as well. So we are finding the derivative of a constant. The derivative of a constant is 0. So the rule that we apply here, the derivative of a constant is 0. On example B, we have our basic natural exponential function, derivative of e to the x. I know this is a hard one. That is good old e to the x. Let's switch the position of the x and the e. On example C, we're finding the derivative with respect to x of x to the e. So I've got a variable base and I have a constant exponent. In this case, we're going to apply the power rule for derivatives. So we take the power down in front, the base stays the same, and we decrease the exponent by 1. So again, we're distinguishing between, in example B, we have a constant base and a variable exponent. So that's an exponential function. In example C, it's just a power function. We have a variable base, a constant exponent. That's when we apply the power rule. On example D, this is the new formula we just learned. It is an exponential function. It's related to b, but it's different because it's a base other than e. So we make a copy of the exponential and then we multiply by natural log of the base. And the last one and most challenging one is the case where we have a variable base and a variable exponent. Now we've talked about this before. Do you know what to do? If you need to differentiate something that has both a variable base and a variable exponent, you should use logarithmic differentiation. But you already knew that, right? So before we differentiate, we're going to take the natural log of both sides. And the presence of that natural log allows us to move the exponent down in front as a coefficient. Now, we didn't differentiate there. That was a property of logarithms. Once we've separated the exponent from the argument, we're going to differentiate both sides with respect to x. So here's our plan. We want to get this differential operator on both sides. The derivative with respect to x of natural log of y, as you've seen many times, is 1 over y dy over dx. On the right side, because we're dealing with the product of two functions of x, we need to apply the product rule. So we have our first factor x times the derivative of the second factor, which is 1 over x, plus the derivative of the first factor times the second one as is. If we simplify that a bit, we end up with 1 plus natural log of x over there on the right side. We can solve for dy over dx by multiplying both sides by y. And then we're going to replace y with its expression in terms of x. So we're going to replace y with x to the x power times 1 plus natural log of x. So the derivative of x to the x looks like x to the x times 1 plus natural log of x. So be very sensitive to the structure of your exponential function, or what looks like an exponential function. On example A, we had a constant base to a constant exponent. Therefore, the derivative was 0. On example B, we had a constant base and a variable exponent, but that constant base was special. It was e. On example C, we had a variable base constant exponents. We needed the power rule there. And on example D, we had constant base, variable exponent. That's an exponential function. And the base was something other than e, so we had to apply our special rule. And then finally, on example E, we had variable base and variable exponent. So we had to do logarithmic differentiation. So be sensitive to the structure of the function you're differentiating. That dictates which rule you apply. Getting a little more practice with these exponential functions, let's work through example 3. The problem is simply find the derivative. So we could label our derivative here, y prime or dy over dx. Again, we have a constant base and a variable exponent. So we make a copy of the exponential function. We multiply by natural log of the base, and we multiply by the derivative of the exponent. Another way to write that, we move that little single constant coefficient to the left. Let's see, what's the best way to do this? Let's try it as 5 times 4 to the 5x natural log of 4. Both of those lines, of course, would be acceptable. On the next one, notice we have a variable base and a constant exponent. So this one requires the power rule. So we're going to have a constant coefficient of 2 that filters through to the derivative. And then we're going to take our exponent, our constant exponent down in front. We're going to keep the base the same, and we're going to decrease that exponent by 1. A good way to write this one is to put the x in the middle. Actually, I like it the first way we did. I'll just leave it like that and call it good. How about example C? Do you notice on example C we have a variable base and a variable exponent? This means we need logarithmic differentiation. So before we differentiate, we're going to take the natural log of both sides. We have natural log of y equals natural log of x to the sine over x. We're going to move our exponent sine of x down to the left as a coefficient, and we're ready to differentiate with respect to x. I'm going to introduce this differential operator to show a change in my approach. I'm no longer just simplifying, I'm introducing a new operation. As always, the derivative with respect to x of natural log of y is 1 over y dy over dx. And on the right side, we need to apply the product rule. So we have our first function sine of x times the derivative of the second, 1 over x, plus the derivative of the first function, the derivative of sine is cosine, times the second function as is. To solve for dy over dx, we will multiply both sides by y. Nothing to simplify here, so I'm just going to copy everything down. And remember, we have one more step to make our derivative explicit. We're going to replace y with its expression in terms of x. So we're going to replace y with x to the sine x. Just going to borrow some space down here. Dy over dx equals x to the power sine of x times sine of x times 1 over x plus cosine of x natural log of x. And that's it. Okay, let's try example D. Derivative with respect to x of 2x minus 3 times x to the 3/2. Clearly we have the product of two functions of x. So our derivative requires the product rule. So we'll write our first function times the derivative of the second. Notice the nature of that second function. We have variable base, constant exponent. That's an ordinary Calc 1 problem, right? So we're going to take our constant exponent down in front, keep the base the same, and decrease that exponent by 1. 3/2 minus 1 equals 1/2. Plus derivative of our first function, which is just 2, times the second x to the 3/2. Let's go ahead and simplify by factoring. Notice we have two terms here. They have in common an x to the 1/2. But in fact, I'll show you a trick here. I'm going to factor out also a 1/2. This will clean up the fractions inside my parenthetical element here. So I'm going to take out the lowest power of x, x to the 1/2. So taking out 1/2 x to the 1/2 from our first term is going to leave behind a 3 times 2x minus 3. And I just reversed the order there to keep my smaller factors to the left. Plus, now remember, I'm factoring out a 1/2. So my ultimate result has to be a coefficient of 2. So if I take 1/2 times 4, that will result in 2. So everything inside this bracketed element here will not have a fraction. Makes it nice and easy to work with. And 1/2 plus 2/2 or 1 gives me 3/2. So we're going to end up with just a 4x there. So simplifying what's inside brackets here, we're going to distribute our 3. We have 1/2 x to the 1/2 times 6x minus 9 plus 4x. And finishing off, we have 1/2 x to the 1/2 times 10x minus 9. Now, look at that and you be the judge. Which one's simpler, this one or this one? If I asked you to analyze the derivative and find critical points, which one would you prefer to work with? Definitely the simplified form. So choose that simplified form or work on that simplified form in preparation for analyzing the derivative. Okay, let's try another example. Derivative with respect to t of cosine of t raised to square root of t. Notice we have a variable base and a variable exponent. So in this case, we are going to need logarithmic differentiation. Also notice the difference in the presentation of the problem on example E as opposed to example C. On example C, we were given the function y equals x to the sine of x. So it was set up as an equation where we could apply the natural log to both sides. In example E, with the differential operator, we don't have a two-sided equation, so I can't just introduce a natural log into the function without being able to balance it over on the other side. So we're going to rewrite this equation as y equal to cosine of t to the square root of t. That will allow us to introduce a natural log to both sides. In introducing it to both sides, you can cancel it out later on. Now, since our natural log is available, now we can move the exponent down in front as a coefficient, and we're ready to introduce our differential operator. Now be careful here, I'm not going to do a d over dx. Our independent variable is t, so we're going to find derivative with respect to t of both sides. So again, we have to be careful on the left side. We're going to differentiate natural log of y to get 1 over y, but instead of dy over dx like we're used to, this is derivative of y with respect to independent variable t. Whoops, lost a square root over here. Okay, there we go. Now we're going to apply the product rule. So we have the first function. Now I'm going to write that first function as t to the 1/2. So we can think about it that way when we differentiate here in a minute. Then we need to differentiate natural log of cosine of t. So we're differentiating a natural log function. So we're going to put the argument of the function in the denominator and the derivative of that argument in the numerator. Therefore, we've differentiated the log. Continuing our product rule, thinking of square root of t as t to the 1/2, the derivative will be 1/2 t to the negative 1/2 times our second function, natural log of cosine of t. Now we're going to have to do quite a bit of algebra to simplify this, so I'm going to take a step to clean this up a bit. I'm going to convert the 1/2 exponent back to radical form. So looking at our first term here, we have negative square root of t. Now we have sine over cosine. We could simplify that to tangent of t. So again, the t to the 1/2 becomes the square root of t. The negative in front of the sine is accounted for, and sine over cosine gives us tangent. Now on this one, we're going to have natural log of cosine of t on the top, and because we have a negative exponent on that t, I'm going to write that t to the 1/2 in the denominator and convert it back to square root form. Now we're ready to multiply both sides by y. So we have dy over dt equals y times everything we have over here. Now, the fewer signs we can write, the better. So I'm going to transpose our two terms here so that we can lead with a positive term. I'm going to call it natural log of cosine of t divided by 2 square root of t minus square root of t tangent of t. The last step is to replace y with its original expression in terms of t, and we'll have our derivative. dy over t dt equals cosine of t raised to the square root of t times natural log cosine t over 2 square root of t minus square root of t tangent of t. So that one was much more involved than example B, for instance. Next, we will examine differentiating logarithmic functions with bases other than e. We've already learned that the derivative with respect to x of natural log of x equals 1 over x. Remember, a natural log is specifically a base e logarithm. So what do we do if the base is something other than e? For example, derivative with respect to x of log base a of x. Well, in the derivative formula, you still see this pattern, 1 over the argument of the logarithm, like we saw in our original formula. But now we have this extra adjusting factor in the denominator, natural log of a. That accounts for the base other than e. Now, let's see where this formula comes from. To find the derivative with respect to x of log base a of x, we're going to apply the change of base formula to log base a of x. Recall that this is equivalent to natural log of the argument divided by natural log of a. Again, that's called the change of base formula. Now, a is a constant, so natural log of a is also a constant. And we can factor constants in front of our differential operator. So we have 1 over the natural log of a times the derivative with respect to natural log of x, which we'll easily recognize from all of our practice is 1 over x. Now, if we clean this formula up just a bit to match its original presentation, we end up with the derivative with respect to x of log base a of x is 1 over x times natural log of a. So the big idea is if you're differentiating a logarithm with a base other than e, you still follow the pattern of writing 1 over the argument, but then you multiply by natural log of the base. The chain rule also applies to this situation. Let's suppose instead of an x, I have a function of x in the argument position. Well, we're still going to write 1 over the argument like we normally do. We're going to have this extra adjusting factor, natural log of a, because of the base of the logarithm, and then we'll multiply by the derivative of the argument. Let's apply this new formula to a couple of practice problems. Example 3, find the derivative. So we can call this derivative y prime or dy over dx. First of all, notice we have a constant coefficient. That filters through to the derivative. And then we're going to differentiate a logarithm with base 3. To differentiate a logarithm with base 3, we're going to take the argument of the logarithm and put it in the denominator, and the derivative of that argument goes in the numerator. Then we're going to have an extra adjusting factor in the denominator, natural log of 3. Now, back up here to our formula, when we were looking at multiplying by the derivative of the argument, another way to think about this formula is u prime over u times the natural log of a. It's an equivalent way of thinking about it, different notation, maybe a little more efficient to execute. Let's try another example. Example B, we have 1 divided by log base 4 of x. So notice we have a quotient here. Now, we can always avoid the quotient rule by rewriting that logarithm as a negative exponent. That denominator, log base 4, can be raised to the negative 1 power. That way, we can avoid the quotient rule by using the power rule. So we'll take the exponent, negative 1, down in front. We're going to keep the base the same, and then we're going to decrease that exponent by 1. Then the chain rule says we need to multiply by the derivative of the base. Well, it's a log with an argument, a base other than e. So we're going to put the argument of the logarithm in the bottom. Of course, its derivative is 1, and we're going to multiply by natural log of 4. Do you notice the notation over here on the left-hand side? On step 1, I rewrote y because there we were just doing some algebra, but then we recognized the derivative step starts here. Now, a good rule of thumb, how do you present your derivative? Use the same type of notation that the original function was given in. The original function was a fraction, so instead of using this negative coefficient, I'm going to rewrite this as a fraction. So I'm going to leave this negative coefficient in the top. We're going to move that logarithm to the bottom. And by the way, you can write your exponent between the logarithm and its argument. And then we have the single factor x. I'm going to move that to the left to make it easy to read, and natural log of 4. So there is the derivative of that original function. Now, one last example here. f of x looks kind of complicated, but we know that we can use properties of logarithms to simplify before differentiating. So I'm not differentiating. I'm going to write my function f of x, and I'm going to rewrite that radical, that square root inside the argument, as a 1/2 exponent. Now, we know that the argument of a logarithm with an exponent can be converted into the exponent down in front as a coefficient, like so. So keep in mind, whenever I moved this exponent right here, that was not differentiation. That was the application of a logarithmic property. So we're still dealing with f of x here. But it was convenient because now both of these coefficients cancel. Then we can further expand this logarithm. We'll take logarithm of the argument in the numerator minus log base 5 of the argument in the denominator. Now remember, you cannot distribute a logarithm across a sum or a difference, so that's as expanded as we can get. Now we're ready to find the derivative, so I'm going to label that over here on the left side. So the procedure for finding the derivative of log base 5 of x plus 1, first of all, I'm going to put the argument of the logarithm in the denominator and the derivative in the numerator like I normally do. But then we have this extra adjusting factor, natural log of the base, to account for base 5. This derivative will look very similar. We'll have the argument in the denominator, derivative of that argument in the numerator, times natural log of 5. Now let's go ahead and take the time to combine these two fractions. The common denominator here would be x plus 1 times x minus 1 times natural log of 5. Now, if we compare the first denominator to the new denominator, we can see we've gained a factor of x minus 1. So if I also multiply that numerator by x minus 1, that one's been updated. For the second fraction, when we compare the old denominator to the new denominator, we can see we've gained a factor of x plus 1. So we need that in the numerator as well. Now, in parentheses on that second term are very important because as you can see here, we need to use our distributive property. And by the way, we're always going to keep our denominator factored. Makes it easier to analyze later on. So the two x's cancel and our derivative looks like negative 2 over x plus 1 times x minus 1 natural log of 5. And that's that.